Welcome back. This is Mr. Keppel. This is part 2 of the ideal gas investigation experiment video. In this video, I'll be showing you how to collect the data for the experiment, as well as design a methodology that ensures reliable data collection. The first thing you'll notice when you open up the PhET simulation is that it's set to Kelvin by default. You're going to want to change that to Celsius. Remember, we're trying to do a historical reenactment where the Kelvin scale hasn't been invented yet. Also, change the pressure to be in kilopascals so that we're using the correct SI unit. In this experiment, what you're going to be doing is adding some particles to the container. I'm going to pick 500 just because it's sort of in the middle. And then the particles will start to fill out through the container, and then we'll be able to read off the temperature and then read off the pressure. Remember, in this experiment, we're varying the temperature and then measuring the pressure in an attempt to create a linear relationship with this graph. The first thing you'll notice when you stare at the pressure gauge is it's wildly fluctuating. It's moving all over the place. So the very first thing that you need to do in this experiment is to design a methodology that will minimize the fluctuations in the pressure. Otherwise, everything in this experiment can be completely controlled. We have beautiful precision in the width of the container. Whatever you set this width to, you know exactly what it is. It's got that decimal point there. We also have pretty good temperature measurement up here. Notice there is no decimal point there. That's going to cause us some problems. But basically, the pressure is the greatest source of error. So you're going to need to come up with some sort of a methodology that allows this pressure variation to be as minimum as possible. And I'm not going to show you how to do that because I want you, the scientist, to come up with your own methodology of minimizing the fluctuations in that pressure. Second thing, so what temperature should we use? When we go to collect the data, we're going to have a range of temperatures that we're going to want to use. So I would recommend doing it between 0 and 100. That would allow you to do increments of 25, so 50 and 75. That gets you to 5 data points. If you want to do more than that, go ahead. If you want to do less than that, no. You have to have at least 5. Now, what that means is that when I go to choose how many particles I want and what volume to use for the container, remember those were the constant variables. Those are the things that are going to be held constant. You get to pick what you want those to be and what you're going to set those to. So pick numbers that make sense. Pick numbers that will minimize these fluctuations. So what you're going to want to do is raise this up to that highest temperature to 100 Celsius. We'll just use that as the maximum. I mean, I guess you could go higher if you wanted to, but I'm just going to cap it at 100. Now, at the highest temperature that we're going to test at, you need to make sure that the pressure for whatever you choose for the container dimensions and the number of particles, that it actually can, the container can withstand that pressure. So notice that if I shrink the volume, it increases the pressure. And if I increase the number of particles, that also increases the pressure. So when you're deciding what to do here with how to minimize the fluctuations of the pressure, just kind of play around with this. Like if I increase the volume, how does that affect the fluctuations? If I decrease the volume, how does that affect the fluctuations? And just kind of come to a conclusion. But whatever you do, make sure that that volume, that width that you've set, and that number of particles doesn't do this. Pop the lid. Because if it pops the lid, obviously you can't collect any data. Furthermore, make sure that you're at 100 Celsius because popping that lid, I'm going to set this to number of particles. I'm going to show you what might happen. So I'm going to set this to 800. Put the lid back on there. I'm going to set this to 800. So I'm doing my experiment with 800 and I'm going along, I'm collecting data. Let's see, let's go to 0. Okay, so here I am at 0. And I've started collecting data. I'm like, all right, here's the temperature, here's the pressure. And I go to the next data point. I go to 25, up to 25. Okay, got it. Write down the pressure. You'll notice that if you go up to 50, the lid pops. And that's bad because you just went through all this trouble of collecting all this data for a situation of a volume and a number of particles that doesn't work. So when you're deciding what to set the volume to and what to set the number of particles to, make sure that you've got the temperature all at your maximum value already. So that way you don't accidentally pop the lid while you're doing the experiment. Let's talk about actually calculating these numbers. So whatever you choose, whatever you decide going with for the volume and the number of particles, you're going to put those here. You're going to put in your number of particles here. Let me make this have a box around it. So you're going to want to put in, you're going to record a number here for the number of particles, and you're going to record a number here for the width. That's what actually you have access to from the simulation. The simulation shows you the number of particles, and the simulation shows you the width of the container. Remember to click this so you can see the width, and there's the number of particles. So what I'm going to do is I'm just going to use a middle value of 500, because that's not I don't want to give it away of what you need to set the container to. So I'm just going to pick 500. You guys will not use 500. 500 is a bad number to use. Use a different number. And I'm going to set I'm just going to go to default. So I'm going to use this default width of 10 nanometers, and I'm going to use 500 for the number of particles when I do this experiment. So my n, that's the capital N, is the number of particles, is 500, and my width is 10. Now, be careful though, because that's nanometers. So I actually have to convert this to nano by raising it times 10. That's what E is, times 10 to the negative 9 power. I've got my number of particles and I got my width. Now, the rest of this is going to be conversion. So notice that our equation actually has number of moles. That's what lowercase n is. And our equation has the volume. It doesn't have number of particles, capital N, and it doesn't have the width. So we're going to need to convert these over to do some calculations to get it to relate to our actual mathematical model. So let's do that now. So the first thing is we're going to need to look up Avogadro's number. So if you go to the IB Physics data booklet, it shows you Avogadro's constant, 6.02 times 10 to the 23rd, 6.02 times 10 to the 23rd, and you'll notice that it's per mole. The reason it's per mole is because if you take a number of particles and you divide by a per mole, you'll just end up with a mole. So there's a very small number of moles in this container because this is a tiny container, nanometers. This is the tiny number of particles. Remember, a mole is like trillions of particles. So we have a very, very small amount of moles, which makes sense. Next, we need to look up what the dimension and the height of this container are. I actually provided it to you guys in the documentation for this experiment that's been uploaded to Google Classroom. The depth is 4 nanometers and the height is 8.75 nanometers. So the depth is 4 nano, negative 9, and the height is 8.75 nano, negative 9. To calculate the volume, you simply need to multiply these together. Width times depth times height. There it is. Now these numbers here, this is what we need to use in the actual calculation. I'll show you right here. In the calculation of R, we actually needed that volume and that number of moles to do the calculation. So that's why we've done this. We've calculated these values out because we needed them later on when we go to find the gas constant. We're going to need those numbers. So we'll just do it now before we do anything else. Now that I've got my constant values set up and I know what I'm doing for this experiment, it's time to show you how to collect the data and how to estimate the uncertainties. First, we'll start with the temperature. So we've already decided on our range of temperatures. So we're going to go between 0 and 100. Now here's the thing though, if I set this to 100, so let's go up to 100. If I set it to 100, that's not exactly 100. There's no decimal point. So to fix that, we have to say, look, I'm only confident that this 100 is within 100.5 and 99.5. I'm not confident that it's exactly 100. So that confidence is 0.5 for the absolute error. We know that if you add 0.5 to this or subtract 0.5 from this, that we're definitely within that range. And in fact, it's going to be that way for all these temperatures because none of these temperatures are ever going to have a decimal point on them. So as I descend here through all the temperature values that we're going to use, you'll notice that there's no decimals anywhere there. Going to 0 because I'm going to start my data collection. Now, the way that I recommend handling this fluctuating pressure is by recording the maximum and the minimum pressure, and then from that, determining the pressure, the best estimate of the pressure, like the middle pressure or the average is what we'll do. So what you need to do is stare at this fluctuating pressure, stare at it until you see the highest value. So I'm going to be looking for, there was 400, 414. I'm just going to call them out. When I see a number that's higher, I'll call it out. So my highest right now is 414. So I'm going to see I don't feel like staring at this for too long because it doesn't have to be perfect. But I still see 414. I'm not seeing anything higher than 414. Okay, so I'll come over here and I'll write down 5414. That's my maximum pressure. And I'll do the same thing now looking for a minimum. I just saw 15. Get out of here. I'm going to stop. There's no point in changing this anymore. Minimum. Okay, 375, 371, 347. I just saw a 347. I don't think I'm going to beat that. So I'm going to go with 5347 as the minimum. Now to find the pressure, let me pause the simulation so my computer stops lagging. Okay, to find the pressure, what we're going to do is take the average of these two over here. So that's C15. That's the maximum minus D15. That's our average. So we know that it's, let me try this one more time. So I'm going to take the average of these two guys there. Boom. Okay, there we go. So 5381 is our average of these two. Okay, I was getting a little bit ahead of myself there. Okay, so good. Now, the uncertainty is what confidence, like what range are we confident that this value is within? Well, it had a maximum potential of 5415 and a potential minimum of 5347. So that means that this value is plus or minus in that range. So let's calculate that range. That'll be let's see, I'm going to take the highest value, which is this guy, subtracted by the lowest value, which is that guy, and that gives me my range. So I know that I'm within. There's a 68 kilopascal range that I'm confident that this number is within. But remember, our average is in the middle of that range. So the actual plus and minus is just half that range. So I'm going to divide this by 2. There you go. So now all you have to do is just do this process for all the remaining temperatures, and then you'll be done collecting your data. That's it for this video. I'll see you guys in part 3.